So welcome, good morning. Today is Friday, January 24th, and we are very pleased to introduce our fourth speaker for the Global Computing Lab seminar. And we have today with us Dr. Dewi Yokelson. And Dr. Yokelson is a postdoctoral researcher at the Lawrence Livermore National Laboratory in California. She received a PhD in computer science from the University of Oregon under the mentorship of Alan Maloney. Her research interests include post hoc and online performance observations and interpretation, as well as analysis in high performance computing application and workflow. She's also interested in performance modeling, with applied machine learning, benchmarking, and performance portability. Today we have Dr. Yokelson speaking about RAJAPerf Performance Suite, performance portability analysis with Caliper and Thicket. Welcome.
Thank you, Dr. Caliper. So that was a great introduction. Yeah, this work was a collaboration between UT Knoxville, Texas A&M, and Lawrence Livermore National Lab, where I'm working. So I will just go ahead and get started. So seems like there's a little. There we go. Okay. So in the thank you. In HPC world right now, architectures are becoming increasingly heterogeneous and diverse. You may have heard of El Capitan, which was just released as the #1 on the top 500 list. But you can see here an example on the left of all of the different architectures that we're running on today, mixes of different CPUs and GPUs. And what this really means is that performance portability models are becoming increasingly important. So when you can write a single source code and then run that across many of these different architectures to continue to get speed up when you port your application, this is why these are extremely important. So some examples of those are OpenMP, Raja, and Cocos. So Raja is actually a library from Lawrence Livermore National Lab, which is in C++ abstractions. And so it enables this ability of writing a single source loop kernel and compile it on and run it on many different platforms. So it supports a variety of parallel patterns and performance tuning options. So many different, whatever your application is doing, what types of kernels it's running, it can support many of those. So that brings us to the Raja Performance Suite. So what's really important is being able to ensure that when you write your application with these single source performance portability models like Raja, that you're getting all the performance that you would expect on your new architecture. So the Raja Performance Suite is a curated set of HPC kernels that allow this comparison as you move architectures. So we have all of these kernels implement that you'll see a lot on the x-axis there, but all of those are the many different RAJAPerf kernels, and they are implemented in both the native or base implementation with CUDA or HIP, and then also the Raja programming model version. So this allows us to compare and contrast the performance for each of these. And then it also we can gather for certain metrics natively to understand how those kernels are performing when we run it elsewhere. So some contributions from this work are presenting on the Raja Performance Suite, or otherwise RAJAPerf, I might say that. So if you get confused, that's why, which is this curated set of HPC kernels. And then integrating RAJAPerf with performance analysis tools to further understand the performance of the kernels. Those tools are Caliper, NVIDIA Insight Compute, and Thicket, which I'll explain a little bit more. And then also just some performance portability analysis of the RAJAPerf kernels across 4 different architectures. There we go. Okay, so I will start with just introducing you to Raja Performance Suite and sort of a little bit more about how that works. So in a nutshell, the Raja Performance Suite, like I said, are these computational kernels implemented with both the base or platform native version and the Raja programming model version. So it's broken down into these different things on the right here. You see a group, which is a subset of kernels from either that originate from a single benchmark, such as Stream, which is a memory heavy benchmark suite, or representing certain types of computational patterns. They're implemented in many different programming models. So sequential, OpenMP target offload, CUDA, HIP, and SYCL. Not every single kernel is implemented in every single programming model, but we have this nice table which will show you sort of which is which. And then we can also, we sort them by which features they have in them, which parallel features, such as atomics and sorts and scans. And then we also report the complexity of the kernel and how that will scale. So having all these and understanding sort of how they fit together is really essential for when we want to do compiler testing, performance benchmarking, platform procurement, right? So when the lab purchases new hardware, making sure that it's performing as we would expect. And then of course, if you're going to port your application to a new hardware, it's really nice to be able to look at these and see how they're behaving, and then you can understand how your application. So some of the groups that are in Raja Performance Suite are the algorithms group. So that consists of kernels focused on specific parallel constructs. So you can see here like atomic, sorts, scans. And then you'll see here again, okay, I can sort of show the photo. Oh, we can't do that. There we go. We have the programming models here that each of those kernels is implemented in, the features that it contains, and the complexity. So, and then the applications group, which is the second group here on this list, are kernels from actual Lawrence Livermore applications. So this is really helpful for us as a lab to understand these are the types of workloads we're running on our machines. Let's see how these kernels perform, and then we can understand better our applications. We have basic patterns. Basic patterns. So these are small, simple kernels that typically present optimization challenges for compilers. You can see in here, there's DAXB, pi atomics, things like that. And we have a communication group. So this is testing different packing and unpacking for MPI buffers. And then we have this LCALS group. So this one actually has quite a long history at Lawrence Livermore National Lab as well. It started as a Fortran benchmarking suite called Livermore Loops, and then sort of gone through a series of different transformations. And now kind of actually became the basis for the original Raja Performance Suite. So these were like, I think these were the first kernels that were part of the Raja Performance Suite. And we can use those to really understand the C++ templates and Lambda expressions that we use in Raja. And then we have the Polybench suite for studying polyhedral optimization. And we have Stream benchmarks, which showcase the memory bandwidth intensive kernels. So you'll see Stream Triad pop up again later in the presentation. Stream Triad is sort of the de facto standard for how much memory bandwidth can you get out of a machine. And so we use that as a basis for comparison with some things later. So I'll bring that one back up. Okay, so again, this is the same figure from earlier. We see across the x-axis many of the different kernels in RAJAPerf. And then we see on the y-axis some of the metrics that RAJAPerf measures for itself. So we see how many bytes were read and written on the bottom. And then we have how many flops were computed. And then we can also see like flops per byte. So that gives us an understanding of sort of the characteristics of each of the kernels. And then if somebody has an application that has similar characteristics to some of these, they can then use these to extrapolate performance for their application as well. So this can be really helpful. Okay, so that was Raja Performance Suite. I now would like to talk about our integration with the different performance analysis tools. Okay, so this is sort of how our workflow looks for understanding parallel performance. So like, we saw how, we know how, a lot of us here probably know how difficult it is to run on HPC ecosystems, right? And to measure performance adds another layer of complexity. So here's our workflow. We have over here in step 1, we have the Raja Performance Suite kernels. So they are annotated with Caliper annotations. So Caliper is our performance measurement tool from Livermore National Lab. And we can basically run these kernels and measure performance metrics when we run them linked to these tools. We can also run them with the NVIDIA Inside Compute to get certain, especially GPU metrics. So that's our step 1. We run the kernels linked to the performance measurement tools. Those generate call tree profiles. So this is step 2. Those consist of the structure of the application. So which functions call other functions, and then as well as performance metrics for that's, for each function and metadata about that particular run. So then those call tree profiles can get loaded into our performance analysis tool called Thicket. Thicket is a Python-based tool that relates basically that call tree structure with the different performance data with like a graph and then multiple pandas data frames. And so pandas, as you might know, allows you to do a lot of different data analysis in a Python environment. And so we're really able to, we have these related graphs and tables that we can then perform a lot of different analysis with to understand our metrics better. So if we want to aggregate things or do statistical functions, we have quite a few built-in statistical functions in Thicket. But another real strong point of Thicket being in Python is that it enables this step 4 of exploratory data analysis. We can integrate and use Thicket with pretty much any other external Python library. And so that opens up the ability to do machine learning analysis with the Python libraries, or a lot of really cool visualization with Python libraries as well. And that will run really nicely in Jupyter notebooks and things like that. So this is the workflow using Caliper, NVIDIA Inside Compute, and Thicket. And if there's any questions, I guess we can do them at the end or during. But so an example of some of this analysis we can do with using that workflow is to understand a kernel's bottlenecks. So there's a lot on the slide, so I'll sort of step you through it. But we did this analysis on the Sapphire Rapids CPU with DDR memory. So we looked at measuring, using Caliper to collect what's called the top-down metrics. So top-down metrics are basically the percent of time that an application is stalled in a certain operation type. And so you can see here, all the top-down metrics are either the 4 categories, main categories are front-end bound, which is things like instruction, like waiting on instructions, bad speculation, which can be like a bad misprediction when you choose the wrong if and predict that incorrectly. Retiring, which is the percent of time or the amount of time spent retiring instructions, and then back-end bound, which is split up for our use case into, well, in general, is split into core bound and memory bound. So core bound implies that it's waiting on compute cycles to come back. Memory bound is that the memories, like maybe there's cache misses, things like that. So we can understand how much percent of our, how much time our applications are spent waiting in any of those instruction types can tell us where the bottlenecks are. So Caliper is able to collect those metrics, and then we're able to visualize those with Thicket. So in this, on the right here, we see on the x-axis are all the kernels. Again, this is for the Sapphire Rapids with DDR memory. And then we see each of our bottlenecks on the Y. We broke this down into memory and core bound. And so basically here we see that the higher the bar, the more severe the bottleneck for that particular type. So we see a lot of memory bound. That's sort of the most common that we typically see, especially for HPC applications. So Yes, so we were able to look at that and identify the bottleneck for each kernel. Another thing that we can look at is the resource efficiency on GPUs. So this one, we use NVIDIA Insight to compute and Caliper to gather the performance metrics. So we needed to also look at GPU hardware counters while the kernel is executing. Just to sort of, for visual purposes here, we split this by the different cache layers. So we have the color is every kernel group that I mentioned, and the roofs are basically the memory bandwidth that we can get, and then the top is the instruction number of instructions that we can do. And so we plot this instruction intensity and for each kernel, which we can measure with those GPU hardware counters. And basically what to note here is that the closer the kernel is plotted to the roof lines, the better we're utilizing that particular hardware. So we can see here the L1 cache is a little bit less, we can't optimize for that as much as we can, as we did for the HBM level. So this gives us ideas of which, okay. So we can get an idea of which kernels we might be able to optimize better. So like in here, we look at, we see polybench. So we think, okay, what can we do to maybe get those closer to our roof lines? So this is helpful, especially on GPUs. Okay, so that was an example of some of the analysis we've done with Caliper, NVIDIA Insight Compute, and Thicket. And now we continue to use those tools, but I'll go into a little bit more of the performance portability analysis. So this was on 4 different architectures, which I'll introduce all 4 architectures in a second, but first I'll talk about some clustering we did on the first one. So the first one was a Sapphire Rapids CPU with DDR memory. So in this case, the kernels are only executing on the CPU. And to understand sort of which kernels were similar, we did this hierarchical clustering analysis. And so this is based on those top-down metric bottlenecks that we identified, looking at which were the bottlenecks for each kernel. We did the hierarchical clustering to regroup them in ways that maybe more characteristically makes more sense than our original logical groupings of like per benchmark and things. So you can see that it's not super important to see which kernels exactly are in which groups. I'll kind of go over that, but they do get mixed up across them. And then you can see the different average metrics for each cluster here on the right. So it ended up with a mostly memory bound cluster. That's 2. 0 is memory and some retiring. 1 is retiring, and 3 is our kind of core bound cluster. I'll go into a little more details next. Okay. So cluster 0 is memory and retiring bound, and that was 43% of our apps group ended up in this cluster. So memory and retiring bound for that group. Cluster 1 was our retiring bound cluster. So this was another 43% of our applications group in the RAJAPerf suite ended up in this cluster. Cluster 2 is our very memory bound cluster. So this one is more memory bound than cluster 0. That was 14% of our apps, 100% of our stream benchmarks, which is actually would be expected, right? Those are supposed to be memory bandwidth intensive kernels. And 80% of those LCALs, or like, originally the Livermore loops group. And then the last cluster was cluster 3, and this was the core bound group or cluster, sorry. And this includes some of our like reductions and atomics. So as I mentioned, the benefit of using Raja is that you can have the same source code and execute it across many different hardware platforms. And so for this study, we looked at 4 different architectures. we used 3 of the different Raja execution backends that are available. The Raja sequential, Raja CUDA, and Raja HIP. And then we just vary basically that when we compile and run our kernels. For this study, we use the same problem size per node of 32 million. And then we looked at so this last bullet, we looked at 2 different CPU architectures. So that's the Intel Sapphire Rapids with DDR memory. So that's the one that you've been seeing the top-down metrics for. And then we also looked at those same CPUs, but with the high bandwidth memory. So the main difference there being much more memory available per node, or memory bandwidth available. And then we also ran on 2 different GPU architectures, the NVIDIA V100s and the AMD MI250X. And really of note here is this column showing the memory per node. We see this increasing trend in the available bandwidth, and we'll see how that affects the kernels. Especially. Okay, so one of the things we looked at was for each of those clusters. So we identified clusters based on the top-down bottleneck analysis. And then we looked at how those clusters sped up across the new architectures. So we can see here, if you remember, cluster 2 and cluster 0 were our really memory-bound group clusters. And you can see that here. So the parallel coordinates plot, I guess on the left, the 5 axes in the box are those top-down metrics bottlenecks that we identified. And then on the right, we have 3 axes that show the speed up as we move to different architectures. And so we can see here we have the 2 memory bound clusters, right? They're higher on this memory bound bottleneck. And then we see the speed up on HBM. So really the only difference here is the higher bandwidth memory. And then for the V100 and the MI250, we have increasingly higher memory bandwidth. And then obviously these 2 are the GPUs. So the memory bound clusters were the two clusters that demonstrated the most speed up across all architectures. So as we alleviated that memory bandwidth bottleneck, we were able to really see the speed up. The retiring bound cluster, so this was cluster 1. So it was able to, we saw speed up for that one on the GPUs, but we didn't see any speed up with just extra memory bandwidth alone on the Sapphire Rapids with HBM. So that was still similar performance on HBM, but with the extra compute cycles on with the GPUs available, we were able to see speed up for kernels in that cluster. And then finally, our core bound cluster. This one had the least speed up on GPUs and also didn't see any speed up on HBM. It did speed up on both GPU architectures, but much less so than the memory bandwidth bound cluster. Okay, so in general, thinking about which metrics can predict the speed up, we did find that identifying the primary bottleneck can be a good initial indication of what speed up we might see when moving to the new architectures. Not all kernels follow this pattern, but it's a good sort of guidepost, I guess. And then in general, the kernels that exhibit the memory bandwidth bound characteristics demonstrated the most speed up when we move to higher memory bandwidth architectures. Okay, so then thinking about the Lawrence Livermore applications, so looking specifically at that applications group of kernels, right, mimicking the workloads that we run at Lawrence Livermore, we kind of thought, what do the bottlenecks that we're seeing imply for those? And so here we have the applications group kernels, and they're colored by the cluster that they ended up in. So if you remember, 0 and 2, the purple and the red are the memory bound, and then green is the retiring bound. And so we grouped them, colored them here by that. We see the memory bound percentage. So this is that, the percentage of that bottleneck on the Sapphire Rapids DDR. And then the next three panels are the speed up across the new architectures again. So, and then a little bit more about what's on this figure. The yellow is the stream triad performance. So I mentioned that way back at the beginning of the presentation, but stream triad again is that sort of how much memory bandwidth can I get out of a machine? So we like to see if ideally, you know, if it's if we can get that same performance, that's really great. And then the red line, so that's the yellow line on these panels, and then the red line is 1x speed up over the Sapphire Rapids with DVR. So so really what we see here is only these memory bound application kernels saw any speed up on the HBM. So none of the ones that are in the green, the retiring bound, hit the 1x speed up or exceeded 1x speed up on the Sapphire Rapids with HBM. But we did see some of them exceeding the 1x speed up line on the GPU architectures. And then the memory bound applications sped up across all of these ones. Okay, so another way of sort of visualizing this is looking at the memory bandwidth versus the flop rate, and then seeing which kernels can take better advantage of these increased memory bandwidths. So here we're seeing the Sapphire Rapids with DDR on the left and the Sapphire Rapids with HBM on the right. And we do see this trend of, see the clusters down here, of the kernels shifting to the right? So these are the same x-axes. We see that the distribution of kernels is moving right, taking better advantage of the memory bandwidth, increased memory bandwidth here. We don't see a whole lot of movement with the flops, right? So the flop rate's on the y-axis, and there isn't much movement up. So that is what we saw for, oh, there we go. Okay. Now, when we move to the V100, we see some movement both even farther right and then farther up. So taking advantage of increased memory bandwidth and also a significant boost in the achieved flops for each kernel. So that's what we see. So movement up and to the right here. And then again here, so this actually was a significantly higher speed up. We had to change the axes. So you'll see that this goes much higher to 11,000 versus 4,000. So for the MI250X with much higher memory bandwidth, we see a lot of movement where the kernels were able to take advantage of that. And we also see the increased flop rate. So yeah, so I guess on here, the memory bandwidth is about 3x for what we were seeing on the V100 nodes. And also the increased flop rate. Okay, so some lessons learned were that RAJAPerf enables us to do this comparative performance analysis across these many different architectures. And then we are able to do this performance measurement with Caliper and NVIDIA and Insight Compute, and do the analysis with Thicket. And this was really helpful for our clustering and bottleneck identification. And then the RAJAPerf kernel performance changes as expected when moving to the architectures that alleviated those specific bottlenecks. So especially with the memory bandwidth bottleneck. And then all of this work is available on GitHub as well if you're interested in looking more. We have some Jupyter notebooks where you can actually recreate a lot of this analysis. So yeah, we have some GitHub links in the top right corner if you're interested in looking at that. I think that's it. Yeah, thank you.